Hello everyone, welcome to lecture 11 of this course. Till the last lecture, we discussed some aspects of lambda calculus. We now study type lambda calculus. So today we are going to discuss types and type systems, background of these concepts, and we are also considered as a case study some aspects of Haskell type system. So now we are moving from the untyped world to the typed world. That means earlier we discussed untyped lambda calculus, and now we are going to study the typed version, that is called the typed lambda calculus. Now understanding the untyped lambda calculus is crucial before we move to the typed version. The pure lambda calculus that we discussed is also called untyped lambda calculus. Untyped in the sense that there is only one type. Everything is a function in lambda calculus. Untyped means there are no restrictions on what can be applied to what. That means we can apply any function to any other function. A term, that is a term, can be applied to any other term. We can write nonsensical terms that go wrong and don't normalize. However, the motivation for studying untyped lambda calculus comes from the following. Church originally wanted a foundation of mathematics. It is for this reason he developed the pure lambda calculus. And we have seen that it is as expressive as the Turing machines. It is the basis for functional programming and the study of computability. However, there are some problems with untyped lambda calculus. We have seen that there are non-terminating reductions like self-application SA, so that is called big omega. So there is no guarantee of termination. This is one aspect. If we have these kind of terms, then it will go on, and there will be no guarantee of termination. It will, in fact, omega, as we have seen, SA will reduce to SA. So there is no guarantee of termination. No guarantee of safety. That means we can apply meaningless things, and it is very hard to reason about programs without types. Thus, types are introduced to restrict lambda calculus so that terms are meaningful and safe. So, it is very important to note that we restrict lambda calculus. Restrict lambda calculus means, that means the language of the untyped calculus will not be considered here in this typed version. That means certain terms will not be considered, they are not considered meaningful. So, this is the meaning of the entirety, the entire lambda calculus that we had. We are not going to look at the entire, that means a set of all terms possible, but only a very restricted terms. That means, for example, we will not consider terms that are non-terminating. So, this is what we mean by restricted lambda calculus. Now, let us see some problems with the untyped lambda calculus. So, we take some examples. So, we have seen the successor function. So, successor function is lambda n, lambda f, lambda y, f n, f y. That means it takes a charge numeral as input and it will generate the charge numeral corresponding to n plus 1. Now, if you take n is 1, we know that the function will work. This we have already seen. It will produce 2. S1 will evaluate to 2. Now here we say that n can be, we do not know what is n could be anything. Let us say arbitrary n. So, we will use it demonstrate for two things. One is n is identity function and n is a first. They are not charge numeral. Let us see how it evaluates 2. So, consider first the identity function. Let us see this nfy part, the body of the function. So, when we are applying this function to n, so that means n will be replaced with this identity function, that is lambda x dot x. So, this part beta reduces to fy. So, successor of id will evaluate to 2. So, this is we are getting fy. So, there is an f here. So, in the other part we had a f. So, fy. So, we are in fact getting f of fy, which is 2, but it is meaningless to say successor of identity. There is nothing called successor of identity. Similarly, let us see if we pass first instead of n as a new charge numeral. So, first is we know lambda x dot lambda y dot x fy. So, this will give us beta reduction, it will give us lambda y dot f, and it will be y is not occurring in f, so it will be f. So, now here we do not even, and outside there was an f, so it will be f of f. So, now this is not even a lambda term. This is not earlier one, it happened to be a lambda term. Now it is not even a lambda term, not even a charge numeral. This is not a charge numeral. So in lambda calculus, there is no way to prevent unwanted parameters to be passed as arguments. We can get undesirable results by passing unwanted parameters. So we need to distinguish between different terms. Now how can we distinguish different terms? Now in any programming language, there is a set of values. So consider, for example, a simple such set. So we have the following elements in the set. Different types of elements are there. So let us color the elements of the set as, so we color them like this. That means these red colors are of one kind, that means they are integers. The blue part, they indicate real numbers, and the green, they are strings. So we can see that very well, that they are representing different types of elements. So now from this set S, which was uncolored, that means everything, all these things look alike. That means they are all members, elements of the set. There is no distinction between them. So after coloring, we say, okay, these are of one type, one color. This is of one color and the another color. This coloring notion is given in Ravi Sethi's book. So consider now addition. So it says add xy is, you are adding these two numbers x and y. X and y are input, you are just adding them. So now with uncolored set S, we can perform 2 plus the string. The string we can perform, since both x and y are values from the set. But this is x and y are coming from this set. So that means we can put arbitrary things. So here 2 plus reta, but this is meaningless. We know that this has no meaning. Now with colored set, we restrict the operation to similar elements of the similar element, that means of the same color. That means we can perform addition on any two elements of which are of red color or blue or green. Thus this will now allow this addition can be performed on these two strings. This two is meaningless. So now we restrict the operation such that either both the elements are colored red or both the elements are colored blue. So coloring, what we are doing in fact in coloring is, coloring of values refers to types in programming language. So in the definition, if you have a definition like add is int arrow in means it takes two integers as input and returns integer types, both the arguments are of type integer and return type is also integer. So here our then as per this definition, both the elements of color red. Red represents the integers that we said. So as per this definition, if we perform 2 plus 2.5, this is not permitted because this is called mismatching of types, because the types do not match. Here one is integer, another is real, so this is called mismatching of types. Now for the successor function, the color of the argument n should be red, that is it is an integer. But is it really an integer? We know that successor function is defined for all n greater than or equal to 0. So n should be of type natural. Thus what we have obtained by doing this sort of coloring and all, that means we are associating some kind of types. This coloring informally we can say as types, or types we can say coloring. So id first then will not be permitted as input to the successor function. By doing so, that is types help in preventing errors. This is what is called safety. Safety in the sense that such errors we can prevent, and that is why we say it is type safe. Type safe means there is no such mismatch. In programming languages, a type is a classification of values that tells what kind of data it is. Example, whether it is an integer, whether it is a boolean or whether it is a string. It tells what operations are allowed. That means we can add two integers, but we cannot add a boolean valued element with a string. This is not allowed. So the types then there are two things associated. One is we said, okay, fine, there are some classification of the elements of that set we did by coloring. That is, we associated the color with some values of the same thing. But then another important aspect is the operations. So one is the kind of the data and what is the type of operations that we want to do. So now if when you say the operations, when you are fixing, so we are doing addition, that means we have to say the argument should be of certain particular type, not of arbitrary type. This is the another important aspect of when we say types. A type thus is a label or logical property of a term that tells us what kind of data or program it is and ensures only meaningful operations are allowed. This is the importance of type. That means the operations that we are going to perform, it is on the types or the appropriate types and not on arbitrary types. Now, how can this be accomplished in a programming language or in lambda calculus, say? So, this is done by a type system. Now, a type system is a set of rules that assigns and enforces types on terms or programs, ensuring computations are meaningful and safe. So, there are certain properties of a good type system. So, for the details we refer to, is an excellent textbook by Benjamin Pierce, that is Type Systems for Programming Language. So, please refer to this book for the details. So, we will just highlight certain aspects. So, first is called soundness. So, soundness means a well-typed programs do not go wrong. Progress is a well-typed term is either a value or it can take a step. Preservation says if a term M has type T at some stage of a computation and a step of the computation takes M to N, then N has type T as well. So, that means we had at some point M has some type and then say we beta reduce it and you go to N, then preservation says it should be of type. So, we will illustrate it with some examples. So, there is another aspect, there is a practical view of type system. So, it allows us to detect errors early, that is at compile time. It restricts programs to those that make sense. It guarantees properties like no add boolean to string, that means you cannot add boolean to string. These types of things are not allowed, that is called soundness. Now, for example, in the Haskell programming language, the functional programming language, it has a very powerful type system and we are going to see some aspects of it. Types are checked at compile time, so fewer runtime errors. So, let us see each one of these properties. The soundness. Soundness says well-typed programs don't go wrong. So, for example, consider this function definition. It says it takes an integer and returns an integer. Fx is x plus 1. So, if x is input, the output will be 6. But if x is hello, that means it is a string, it will be rejected because it is defined for int. So, it takes an integer return, it is not taking a string, so then it is rejected. It is called a compile time error. Progress says a well-typed term is either a value or can take a step. Now, let n be a charge numeral, then successor of n beta reduces to another charge numeral. Here the step is a beta reduction. A step means a step that transforms one to the other, a computation. It is like a beta reduction. Preservation, if a term M has type T at some stage of a computation and a step of the computation takes M to N, then M has type T as well. So, let us consider the pair. So, this is a pair, we have X and 2. The first component is of type NAT and the second component is of type bool. Now, at we suppose we perform FST of this pair. FST we know will give the return the first component of the pair. So, it will give X. Now, the type of X has not been altered, it has been preserved. So, this is what is. So, now we are going to discuss some type rules. So, we are trying to address the question, how can we assert that an expression E has a type T without evaluating the expression. So, the idea here is we are going to discuss this informally. Later, we are going to consider a formal way of looking at it. So, first we set the types of simple objects. So, when we say simple objects, we mean, say for example, when we talk about lambda calculus, our terms were built from x is a variable, lambda x dot m, and we had mn. So, here the simple object would be a variable and a complex object would be an abstraction. So, lambda x dot x, this would be called a complex object. So this is what we mean by simple objects. So if I consider arithmetic expression, so 2 plus 3 multiplied by 5, so the simple objects are 2, 3 and 5. And when we apply the operators on all this term that we have overall, that will be called the complex objects. So what we are doing, first we set the types of simple objects. Okay, let this variable x is of some kind or some type. Then we said 2 is of some type or some kind. Next, we give rules for operation on simple objects. Remember that we said there are two things. One is the type of this thing, this type of whatever we say, we can say variables, and then we see the operations. What are the operations that we are going to perform on the simple objects, thereby resulting in a type of a complex object. So for example, if I know the type of this variable, the 2 is a constant 2 and 3 and 5, then I would like to say, okay, what will be the type of this complex object? That means 2 plus 3 multiplied by 5. This is what we are going to see. So consider this arithmetic expression. So it is E is 2 to the power of 100 plus 5 multiplied by 8 to the power of 50. So here we are not allowed to evaluate this. If we are allowed to evaluate, then 2 to the power 100 will evaluate to some number, then 5 multiplied by it will give, so addition will give me one number. Then I can say this number is n, so whether it is of certain type or not. We are not doing this way. We are saying without evaluating this, how can we say whether E has certain type? So first we are going to give types of the constants. So these are the symbols, the 2, 100, 5, 8 and 50. Here these are the simple objects. So let us say these are all of type natural numbers. Next, the rules will correspond to the operators. So here we have the operators are, one is plus, another is multiplication, another is exponentiation. So the idea is we present it in the form of a numerator denominator structure. The numerator is called the premise and the denominator is called the conclusion. So you may think of it as an if. This is also if, this is then. It has to be read like if all the conditions given in the numerator, they are satisfied, that means they are true, then we can infer or we can conclude that whatever is given in the denominator, that is also true. This is the rule. So what then this says? It says, we are using this notation, so we will read it at x is of x has type nat, or x, this object we are associating a type called natural numbers nat, and we are doing the same for y. So x is an object that has a type nat, y is an object that has a type. If I perform an operation on these two natural numbers, that means this op can be either of any one of these operators. So there are in fact 4 rules. Here we have written just op, it will be one for each, one for addition, one for multiplication, one for exponentiation. So there are in fact 3 rules. There are 3 rules. There are 3 rules. So that means if x is natural, y is natural, x plus y, one rule will be x plus y will also be natural, and so on. So it may be x times y will be natural, and x exponential y, that is also natural. So this is what is given to us. Now we are trying to find what will be the type of this expression. So we proceed as follows. First we break this expression and rewrite it in a simpler way. So we say it will be like E1 plus E2, where E1 is this part, E2 is this part, and E2 is again like this. So we break up into terms like this. It contains only one operator. Now let us claim that this expression E the type of this expression is net. So now we try to construct the tree in a, this is called a deduction tree, in a bottom up manner. So we know the rule. So now what we are now doing, we are proceeding from the denominator. The rule was numerator to denominator, and we are proceeding in a reverse direction, that is from the denominator to the numerator. That means what? Suppose we say this E expression is, the type of the expression is net. So E1 plus E2 is net. So we have to prove this. In order to prove this, we move this way, bottom up. Now if this rule says that E1 should be net, E2 should be net. So this is an instance of the rule. Other one was a placeholder. And here we are creating an instance. That means we are supplying x with E1, y with E2, and this E1 plus E2 as this. Now we need to show this. Now what we know, E1 is 2 to the power of 100. So 2 to the power of 100, if this is claimed to be net, then we have to see this one is of type net and this one is of type net. Indeed, this is the case because we have already defined that all the constants are of type net. So this part is given. So hence this part of the proof is done. E1 part of the proof is done. So we have to proceed similarly. So then the other part will be then E4. This part similarly we get to know that this is also of type net. And if we do the accordingly E3 times E4 multiplication, it will be 5, E3 is 5 and this is 4. And E4 already we have proved, so hence this part is also proved. So that's what we have now. E1 we have proved it to be net, E2 has been proved net, this was required, and then this one is, so we have established that this is indeed E is of type net. So now if you fit together all the parts, so you will get a tree like this. So you will get a tree like this. So again you may get a tree like this. So here the leaf nodes, this will be the leaf nodes of the tree. This is the root and this is the leaf nodes. Leaf nodes means these are the constants, whatever we have defined for the elementary simple objects. For the simple objects, whatever was, you cannot proceed any further. No rule can be applied here. So you stop here, and this is called the deduction tree. The structure of the deduction tree will look like this. We will see later other complicated examples. Now let us proceed in the same way and try to see what will be the type of 2 plus 2. So now you are adding a string to a natural number. Now again, as before, let us claim that 2 is net. But then if we do this way, so it will be 2 plus true. We are claiming this to be net. Then 2 we have to prove it is net, and true we have to prove it is net. Now this part we know it is already given. This is not given. This is 2 is not of type net. It does not match anything. So this part is done. So we are not able to complete the proof. That means this expression is meaningless. That means the type system in this way, it will recognize that there is a mismatch of types. It is expecting this argument to be of type net. And it has inferred that this true that we have supplied here, it is of type bool. And bool and net, they are different things. So hence there is a mismatch. Now let us see another rule for if. If program we know, it looks like if B then C else D. So the important things here are these parameters B, C and D. And let us say we want to say what will be the type of B. That means we should first identify or associate types of simple objects. Here simple objects are B, C and D. B must be of type Boolean. So we say if B is Boolean, let us say C is of type T1 and D is type T1. Now when B is true, we know answer will be C. That means the type returned for if will be T1. If it is false, type will be T2. Now if program cannot have different types for different inputs. So this is not meaningful. So T1 and T2 they must be same. So let us say their type is T. So then the rule comes that the type of if will be if T, provided B is a boolean, and these two things C and D, they are of type T. If B is type boolean, C and D are of some type T, they are same, they are of same thing T, this is bool, then the whole thing evaluates to T. So this is the rule for if. So that means if B, if your program you have written here, if it is not evaluating, if this is the guard, it is not evaluating to true, it is evaluating to some number, it is not true or false, then that will say it is a mismatch, and that is how we get the error messages in when we compile our programs. Another example, we will see many such instances of this one. This is very important, or we are going to use this most of the time. Function application comes from MN, lambda calculus, we said MN. So if a function takes as argument of type T1 and return type is T2, then the input should be of type T1, then X should be of type T1, then Fx is of type T2. Then if you want to do Fx, the argument supplied should match with the defined input of the function f. Then we are going to get f of x. So we are going to discuss now the type system of Haskell. So static, it is static in the sense that types are checked at compile time. So many errors are caught before the program runs. It is strong in the sense that any type errors in definitions and expressions are found before evaluation. This we have seen. Now type inference. That means we often don't need to write types. The GHC compiler figures them out. For instance, if we write square x is equal to x times x, so Haskell infers it as, Haskell will give this square colon, that means this is a type signature it is returning. It is say num a implies a arrow a. That means for any type, num is a numeric type class. So it says for any type A that belongs to the type class numeric, square takes an A and returns an A. That means the input will be of type A and the output will be of type A. So in numeric class, actually some types that are applicable will be written there. That means, say for example, integer, int, float, all these things are written, and the operations that can be performed, they are all written in the specified in the type class numeric. So this way there are other type classes in Haskell. Now how is this inferencing done? So the operator star works for any type that belongs to the numeric type class, say for example integer, int, float and double. So it is not just integer, int, it is for any of these. So that is why it says that if A belongs to the type class numeric, it will take a input of type A and returns an input of the type A. So this is a generalized version that it has given. It has not given at int A arrow A. It has not reported this way. It is saying it is applicable for any such A, provided A should be a member of the type class numeric. Okay. Let us consider the second example. So the second example says the function is compose f gx is equal to f of gx. That means g is applied first to x and the result that we have obtained, f is applied onto it. So Haskell infers that compose is a type is b arrow c arrow, this is part 1, this is part 2, a arrow b, then a arrow c. Now how is this obtained by, how is this inference done? So we have seen the rule for function application. Function application rule says if f is of type t1 arrow t2, x is of type t1, then f of x will be of type t2. So here x is the variable. So let us say x as type a. That means x as type a. That means this f it is inferring, it is first assigning, say x is a. Then what it does, it says then f in this case g, this must be a arrow something, because this is a, this must be a, so this must be something, then this something is in a general sense it will say b. So this is the most general thing that it has obtained. So it start with x and say now we are doing function application. So I must say a arrow b, it will be a arrow b, then the resultant will be a arrow b, b will be the output of this fx. That means gx return type is b. So g it has inferred a arrow b. This part we have done. G's return type is b means this is the input of f. That means this is the input of f. And again similarly f's return type in general I will say c. So then since c is the output of f, that means it is output of compose. So that means this is we have obtained. And in this way the type system has inferred that compose has type this, although it is not explicitly specified. This is called type inferencing. Now how is a type error detected? Now we consider some examples like using the rules that we have seen. Say for example 1, so we say suppose we say 5 plus, now we can do using type rules. So as discussed for the example of NAT, so addition say is defined on integers. Say addition is defined for integers. Now it says that means both of them should be integers. That means here the inferred type, so first it will infer this type. Inferred type of hello, this is a string. Inferred type of 5, this is int. Expected type as for this int, if int is defined, plus is defined this way, then it will be the second argument should also be int. So there is a mismatch with the expected type and the inferred type. So there is one is the expected type. Expected type comes from, because from 5 it infers, from plus it infers that it is either it will be say int arrow int arrow int. That means both should be integer. Expected type is integer, inferred type is string, so then there is a mismatch. That is an error will be reported here. Now let us say we have consider the successor function. So successor function is n is equal to n plus 1. So that means successor functions type will be nat arrow nat. Now when we give successor true, so recall that we tried to do this the first example. Successor true, how it will work? So that means successor is this function suc is of type function rule we are going to apply nat arrow nat, and the argument true it will infer something, and then it will give successor of true to be something. So here true it infers it to be bool. It expects nat, expected value is nat. So it cannot match these two. So then this will not proceed and it will say there is a mismatch of the inferred type, and the inferred type of true is bool and expected type is nat, so it nat or int, and it will give that there is an error. Next consider we have P or Q and. So this is a logical or, this is a and. So that means this should be bool, Q should be bool, and R should be bool. Now what if R is equal to 2? So here the inferred type is of R is int. Here when it comes evaluate this part, check this R, is the inferred type is int, expected type is bool. This does not match, so there will be an error. So there will be an error. This is how it is going to detect an error and report in this way. The inference engine works this way. Now we study polymorphism. So we refer to this is a seminal paper by Cardelli and Wagner. So polymorphism means, that means either a name or a function is applied to different types. So one type of polymorphism is parametric polymorphism. This is called the purest form of polymorphism. Now the functions work for any type. So we have already seen functions like length. Length function we have seen length of a list. So length of a list. So say for example, if you have 1, 2 and 3, it is a list of integers. The output will be length will give us 3. Now if we change it to some other type also, if we make it a character, this will also give 3. And if we make it strings, this is also, it will also work and the answer will be 3. So the length function works for all lists of all types. List of integers, list of strings, list of char and so on. So this is called parametric polymorphism. That means the parameter is, it is for all A, for all types A. Length has type list A arrow int. This is called parametric polymorphism. That means the same function I can apply to types of different kind. That means list of integer and so on. Next is the reverse function. That means if we take a list, reverse function will reverse it. 1, 2, 3 will give us 3, 2, 1 and so on. So it will work not only for integers, it will work for any type. So here also it is for all types A. So it is polymorphic. Now we have seen the head function, head and tail. Head, it will give the head of the list is the first element and tail is the remaining part. Now head is, input is a list of say type A and it is an element of type A. So if it is a list of integers, it will give the first integer of the list. If it is a list of strings, it will give the first element of that list. That is also a string. So this is a head. It works not only for integer, it works for any type. So this is also for all. Tail is, it takes a list and returns the list. So here tail will be 2, 3. Likewise, it can work for any types. 2, 3 can be replaced with any types, it will still work. So it is for all. Now we have also seen this plus, that means you are combining two lists. So if I have 1, 2, 3 and if I combine with it 4, 5, so this will give us 1, 2, 3, 4, 5. So this plus plus again, it takes two lists as input of some type A, then it gives A. So this is a list of integers, this is a list of integers, we have obtained a list of integers. It can work for all A. So this means polymorphic. Now polymorphism also appears in another way called ad hoc polymorphism. Ad hoc polymorphism, we may have either overloading or coercion. Overloading means the same symbol or name is used for different operations. Say 2 and 5, so we are adding 2 and 5, 2 plus 5 and we are doing 2.5 plus 3.5. Suppose they are both allowed. So this means the operator plus is overloaded. That means it is defined as int arrow int arrow int or float arrow float arrow float. These two things are there. So when they find that it are adding float and float, it applies this. When it is inferring that these are integer, then it applies this. So we say the operator plus is overloaded. Now suppose one of the arguments is different type. So one is of type int and the other is of type float. So how will this inferencing be done? So one option would be, so a literal like 5 is of type int as well as of type float. We can say that the literal is of type float as well as of type int. So here 5 is overloaded. 5 is overloaded. And then that means when we are doing 5 plus 2.5, 5 plus 2.5, that means 5 is now also float. So float and float we are doing. So that will create no problem. Another option would be to coerce the type into float. So that means if 5 integer we convert to 5.0 and now 5.0 is float and this we can do. So this depends on the programming language design. So option 1 is Haskell uses option 1. C language uses option 2. Now we see type signatures. A type signature describes a function's contract. So for example, consider the map function. It takes a function as an input and a list. So it is a list of type A, and the function is taking an element of type A and transforms it to an element of type B. That means output will be a list of type B. This is what function is. So the output will be a list of B's. So we have seen, for example, say if I want to do +1 on the list 1, 2, 3. So this list we are going to get 2, 3, 4. So it is of same type. Here this and these are same. Now if we want to say make it convert to character, so this will be a list of type character. So map is, so this signature says what is permitted and what is not permitted. So that means, for example, here the input is type integers, but the function type says it is not, say this is int. So you have a list of integer, but this is something else. So this is car arrow int. Now this will be mismatch. Here we have a list of integers. This function takes a character as an input. So this is not mismatch. So there will be a mismatch. So this is a way to infer that there is some errors in the program. Now if we do not provide type signature as seen in the earlier examples, it may infer the type. So the type that it infers is called an unintended general type. It will always take a general type, and that may be unintended. So for example, if we do f of xy is equal to x plus y, so the inferred type is a numeric a. If a is numeric, then the type will be a arrow. So that means it is giving a general, not only integer. It is saying any type A that belongs to the numeric class, then it will be a arrow A. But suppose we had meant only integer, so it would be better to write int arrow int arrow int. So that is the. So we summarize here that we have discussed some aspects of types and type systems. We are given the background, and we have discussed some features of Haskell type system. So you are requested to look at these books. So for different things like coloring part, you can refer to Ravi Setty's. For Haskell part, this is a very nice book by Simon Thompson. And for polymorphism, refer to this seminal paper by Cardelian Wagner. And type systems, all the properties and all, we refer to Benjamin Pierce's book on type systems for programming languages. So we stop here. Thank you for your kind attention.